Hi everyone, this is the even Fibonacci numbers problem by Project Euler. The link to this problem will be in the description. The problem says each new term in the Fibonacci sequence is generated by adding the previous two terms. By starting with 1 and 2, the first 10 terms will be 1, 2, 3, 5, 8, 13, 21, 34, 55, and 89. By considering the terms in the Fibonacci sequence whose values do not exceed 4 million, find the sum of the even valued terms. And this here is our answer. So let's first reword the problem. So the problem is given x, find the sum of the even valued terms of the Fibonacci sequence less than x. And we're rewording the problem just to make it more of a coding challenge. So the constraints are that x can be greater than or equal to 1, but less than or equal to 10 to the power of 9. This is the overview of our solution. We're going to get every Fibonacci sequence number less than x, and for each even Fibonacci number, we will add it to our sum. Let's do a walkthrough. Given x equals 4, these are our Fibonacci numbers. So 1, 2, 3, 5, and this is just something I copied from over here, right? And it continues. So how do we calculate the Fibonacci numbers? We start with a previous Fibonacci number equal to 1 and our current Fibonacci number equal to 1. Then we check, is 1 less than x, our given x value? In this case, yes it is. Then we check, is 1 an even number? It is not, so we do not add it to our sum. Now we need to get the next Fibonacci number. So our next Fibonacci number is 2, but how do we calculate that? So we calculate that by taking our previous Fibonacci number and adding our current Fibonacci number. So in this case, that will be 1 plus 1 equals 2. And that's how we get the next Fibonacci number. So let's go ahead and set our previous Fibonacci number equal to our current number. Well, since they're both 1, nothing changes. So let's set our current Fibonacci number equal to our next Fibonacci number. There we go. So now our current Fibonacci number equals 2, which is the next Fibonacci number sequence. So we check, is 2 less than x? So yep, 2 is less than 4. Now we say, is 2 an even number? Yes. So we add it to our sum. So now our sum equals 2. Now, once again, we get the next Fibonacci number. So next Fibonacci number equals current Fibonacci number plus our previous Fibonacci number. So it's going to be 2 plus 1, which equals 3. So now we have our next Fibonacci number. So let's set our previous Fibonacci number equal to our current Fibonacci number. So this 1 is going to change to a 2. And then we will set our current number, our current Fibonacci number, equal to our next Fibonacci number. So this will change to 3. Now that our current Fibonacci number equals the next number in the sequence, we will check, is 3 less than x? Yes. Is 3 an even number? No, so it does not get added to our sum. So we continue this again. So one last time, get the next Fibonacci number. It's the current Fibonacci number plus the previous one. So it's going to be 3 plus 2, which equals 5. And then we set our previous Fibonacci number equal to our current Fibonacci number, which is 3. Then we will set our current Fibonacci number equal to our next Fibonacci number, which is 5. So now our current Fibonacci number equals the next number in the sequence. And we check, is 5 less than x? Nope, 5 is not less than 4. So our sum is going to be equal to 2. So go ahead and pause the video, Try to solve this on your own, and then we will solve it together. So I will be coding the solution in Spring Tool Suite. Now this method will execute our solution, and it's going to execute where x equals 1, x equals 5, and x equals 4 million. So we know that when we execute for 4 million, we are expecting this number. And we get that from the problem, right? So 4 million, the answer is this. So that's our expectation. And if the x is 1, we should expect 0. If x is 5, we should expect 2. Let's go ahead and jump into the code. So our sum is going to start out as 0. And now we need to set our current fib number equal to 1 and our previous fib number equal to 1. And we're going to say while our current Fibonacci number is less than x, we will check, is the current fib number, is it even, right? So if a number is even, it's evenly divided by 2. So if an even number, when you divide it by 2, there will be no remainder. So if that's the case, we will add that current Fibonacci number to our sum. After we've checked and added it to the sum, we want to calculate our next Fibonacci number. And that's going to be equal to our current Fibonacci number plus our previous Fibonacci number. Then we will update our previous Fibonacci number. That's going to be equal to our current Fibonacci number. And lastly, we update the current Fibonacci number, which equals our next Fibonacci number. Okay, so once these numbers are updated, it will then check again, is the current Fibonacci number less than x? Is it divisible by 2? If so, we add it to the sum, and then we get the next Fibonacci number. We continue doing that while the current Fibonacci number is less than x. After that, we return the sum. So let's execute this code. And we get our expected values of 0, 2, and this large number. You can see that it matches up here. Cool. So go ahead, pause this video, and solve for the time complexity and space complexity of this solution. So time complexity is asking what is the relationship between our given input, x, and how long it takes to run this method. So if we look, regardless of our input, this is always happening. So this is constant. Same with this, returning the sum, that's constant. It doesn't change depending on our input. But this right here, this while loop, does change dependent on our input. So the greater our x value, the more times this while loop will iterate. But how do we describe that? How many times is our while loop iterating? Well, this while loop iterates through every Fibonacci number less than x. So how do we calculate the Fibonacci numbers of, like the amounts of Fibonacci numbers given a value x? So there's something called the Binet's formula. Now this formula allows you to calculate how many Fibonacci numbers there are given a value n. So that is going to be our time complexity. Our time complexity is the Binet's formula. So the formula right here, if we write it in big O notation, it looks pretty bad. So it's better to just say our time complexity equals the Binet formula, the number of Fibonacci terms given n. Now for our space complexity, and we're asking what's the relationship between our input and how much space is being used. So if we see we have 3 variables here and another variable here. So these variables always get declared regardless of what our input is, regardless of the size. And this one, this is O of 1, because even though it gets created with every while loop, it also gets destroyed with every while loop. So there's only ever one next fib number in memory at a time. So our space complexity is going to be constant. It's going to be O of 1. And that concludes this video. If you guys have any questions or feedback, please let me know in the comments. Thank you.